Why do we always hear a buzzing sound when near a transformer? In the last video, we learned about the manufacturing process of transformers. Actually, its structure is very simple, with two main core components inside, the copper coil winding and the iron core. These are immersed in a metal casing filled with insulating oil. How does this seemingly simple combination achieve the functions of stepping up and stepping down voltage? Before understanding its working principle, let's briefly introduce the function of a transformer. For example, a power station needs to transmit the electricity it generates to residential areas at a certain distance. The station will use a step-up transformer to increase the voltage and reduce the current. This is because the resistance and inductance on the transmission lines can cause power loss. But according to Ohm's law states that increasing the voltage can reduce the current on the transmission line, and lower current can decrease inductive losses on the line. By increasing the voltage, power loss is reduced. Also improves transmission efficiency. But when the electricity is transmitted to the residential area, for safety reasons, our electrical equipment uses relatively low voltage, so a transformer is used to reduce the high voltage to a level suitable for residential use. This is a function of a transformer. It can step up and step down voltage. When you pass an electric current through a wire, it will induce an electromotive force, which will create a magnetic field around it. As the direction of the current changes, the direction of the magnetic field will also change. By winding the wire into coils, a stronger magnetic field can be formed. If we place a similar coil nearby, the magnetic field it generates will, in the second coil, induce a current. The key part here is the magnetic field, which continuously changes polarity and strength. The changes in the strength and direction of the magnetic field constantly disturb the free electrons in the secondary coil, forcing them to move and form an induced current. This movement is called electromotive force. However, this design is not perfect because the magnetic field of the primary coil does not completely cover the secondary coil, leading to magnetic field waste. Therefore, engineers place a ferromagnetic core between the two coils in the loop, which guides the magnetic field along the path to the secondary coil, so that they share the magnetic field. This design makes the transformer more efficient. The principle of a transformer achieving step-up or step-down is not complicated. According to Faraday's law of electromagnetic induction, the voltage in the secondary winding depends on the change in magnetic flux in the primary winding. The magnitude of the magnetic flux is proportional to the number of turns in the winding. When the number of turns in the secondary winding is greater than that in the primary winding, the transformer achieves a step-up. Conversely, if the number of turns in the secondary winding is less than that in the primary winding, the magnetic flux and induced electromotive force in the secondary winding will decrease, resulting in a lower voltage in the secondary winding. In short, by adjusting the ratio of turns between the primary and secondary windings, a transformer can achieve voltage step-up or step-down. So where does the buzzing sound from a transformer come from? It's because the transformer's core is made up of stacked silicon steel sheets. The repeated changes in the magnetic field cause magnetostriction, leading to the expansion and contraction of the transformer core, which results in the buzzing sound. A three-phase transformer is one of the most commonly used types of transformers. It has three pairs of windings inside, but in actual transformers, its three pairs of windings share a single large core. In this setup, the coils are usually arranged concentrically, with the lower voltage coil on the inside and the higher voltage coil on the outside. Each set of coils is insulated from each other. Power transmission is completed only during the magnetic induction process. In terms of transformer winding connections, a common method is to use a Y connection on the high voltage side. Each coil terminal on the high voltage side is connected to the terminals of the other two coils, forming a star shape. The low voltage side uses a delta connection, where each coil terminal is only connected to the terminal of the adjacent coil, forming a triangle. However, in step-down transformers, it is the opposite. The high voltage is in a delta connection, and the low voltage is in a Y connection. Transformers generally come in two types, dry-type transformers and oil-immersed transformers. The transformer windings immersing in insulating oil can provide insulation and cooling effects. When the transformer is fully loaded, the resistance and magnetic loss generated by the windings convert into heat, causing the temperature to rise, and the insulating oil can transfer this heat to the external radiator. Cooling fans are installed on large transformers for cooling, and this on top of the transformer is the auxiliary oil tank, functioning similarly to a car's auxiliary water tank. When the oil temperature rises, it expands and flows to the auxiliary oil tank to relieve pressure, connecting through pipes to the bottom. This is the pressure relief breathing device. Inside, there is filtering material that can filter out air, moisture, and dust impurities, extending the transformer's lifespan. After all, this kind of large power equipment is really expensive.